Okay, this is part 2 of the rational functions review. In this portion of it, I'm going to talk about the graphing that we have here. All right, now I'm going to start with my opinion of this. It's incredibly easy. Okay, these might be different functions that you haven't worked much with, but this is incredibly easy to graph. And if you just follow the rules that I outline here, everything should be fine. Okay, so this is our template. Okay, this is our template for graphing, and you can see that there's not much in there. One major thing is there's no b values. We're not multiplying anything directly to the x. We're going to do a values, h's, and then k's for it. Okay, place you start are your h's and your k values. These are going to give you your asymptotes. The denominator part of the fraction is going to give you your vertical asymptote because it's going to be an x equals number. That would go there, and that's going to draw a vertical line. This is going to give you the horizontal asymptote, the shifting up and down. So if you can place those lines first, the rest of the graph builds around it, and it's pretty straightforward with it. Okay, remember the vertical asymptote is what's making the denominator 0, so I need to take the opposite of that number, which is going to be -3. And on my graph, you can already see I have a vertical asymptote drawn at -3. Yes, when graphing, we want you to draw, there it is, we want you to draw the vertical and the horizontal asymptotes, preferably as dashed lines so we know that that's what they are. If you happen to have multiple colors, sure, go with it. Okay, but I need to see that vertical asymptote and I need to see the horizontal. Now the horizontal asymptote is just whatever that number is. Whatever's out there at the end, -1, okay, draw a line at -1 and there you are. By the way, this point right here, that point is called the point of symmetry, and that might be necessary for a different problem. Just make a note of it. The point of symmetry is where the vertical and horizontal asymptotes meet up. Okay, the rest of the graph is going to be built around that. Now let me talk about some kind of simple things here. Generally in these functions, you've got 4 kind of like quadrants, and they're going to be around the point of symmetry. So that doesn't have to be an origin, but they're around it. If it is a positive graph, okay, if this main portion over here is positive, the graph is going to exist in these 2 corners. They're going to be diagonal from each other, called catty corner, but you're going to be in the first quadrant area and then the third quadrant. If you happen to have a negative, that is going to flip everything technically upside down. It might look like you're flipping left to right, but this part flips down and that part flips up and you end up here. So the fact that I got a 6, and that's a positive 6, that tells me my graph is going to be in these 2 areas here. Okay, now it's just a matter of collecting a couple of points so that you can graph. The way that I approach it is I look at that 6. I'm thinking of the 6, and I'm going to break it up into factors. Okay, the 6, obviously factors that it has are always going to be 1 and that number, so I could do a 1 and a 6. Okay, but I can also create a 2 and a 3, which gives us a little bit more freedom now that we've got these things. Okay, so if you had a parent function and nothing was shifted, if nothing was shifted, this would just be 6 over x. That's all you'd have. And you could plug in any of these numbers and in return get back the other one. If I plugged in a 2 under the 6, 6 divided by 2 is 3. Right, or plug in 3, I get a 2. So what I do now is I pretend that this is the origin. Just pretend. This is the origin, and then I use these factors to plot other points. So now I'm going to take the 2 and the 3, and imagine if I plugged in a 2, I'd get back a 3. So it's not the actual coordinate 2, 3, but everything's been shifted over from where 2, 3 would have been, and now it's here. Now I can also plug in a 3 and get back a 2. But then you've got this other one as well, so we're getting a lot out of this graph. You can do a 1 and a 6. I can go over 1, and then I can go up 6. Okay, and I can go over 6 and up 1. Now for the test, you're only going to be required to do 2 per side, but depending on the type of number you have to work with, like how large it is and how many factors, you could get a lot of points. You're going to notice I missed that one. But I put a dot there, so it's pretty obvious that that's the one that I wanted. You can try and do a little bit better. Okay, on this side, not going to get as many, right? I don't think so. I can go 2 by 3, I can go 3 by 2, 1 by 1, 2, 3, 4, 5, 6. I get 1 more on the grid that I had there. Okay, but I still have more than what's required. Okay, and that's pretty much it. You have the asymptotes. Think of them as a magnet that the graph is being pulled to, but it never actually makes contact with it. Now how it actually kind of bends in the middle, just have a couple of points that you're passing through and everything should be fine. All right, then all this stuff should be pretty basic just to answer. Some of it you can do just using the function itself, but a lot of it just appears when you're doing the graphing. The X-intercept, you have one right there, which is at 3. Okay, the Y-intercept is over there at 1. The domain and the range, these are coming from the asymptotes. The domain would be all real numbers, except that you got this vertical asymptote like right down the middle as you go left to right. So the answer is going to be negative infinity up until you get to that vertical asymptote. Okay, and you use an open interval, and then you pick up after it, and you go on to infinity. And that's the general structure of the domain, and also what you'll see for the range here as well. You're going to have a negative infinity to something, that value off to infinity, but it's going to break where you get that horizontal asymptote, which is at -1. So again, you should not be missing any of these problems. Okay, if the points aren't exactly at intercept values, you can always go back to the idea that x-intercept is when y is 0, so you can set it equal to 0 and solve it, or the y-intercept is when x is 0, which means you can just plug in a 0. I mean, you can take a look at that, and if you want, if you plug a 0 here, you get 6 divided by 3, which is 2, and then 2 minus 1 is going to give you 1, so you get that number. So there's a couple different ways you can get around it, but get them right. Okay, just get them right. All right, 4. This would be a little bit harder to graph because you end up in these unusual kind of fractional places. So you're not being asked to graph it here. What you are being asked is just to identify from this equation where the vertical and the horizontal asymptotes would be and what the domain and the range would be. Okay, which are essentially the same thing, right? The vertical asymptote is what's going to break your domain up, and the horizontal asymptote is where the range is going to be broken up here. Oh, my little template over here. I wrote down some stuff you don't really need to know, but let's see how I... Okay. All right, so I got a little bit extra stuff that you don't really need to know, but I'll talk about it anyway just because it's good to do it. Okay, the vertical asymptote for this guy is still going to come from the denominator, because vertical asymptotes is when this function is undefined. So if I just set the bottom equal to 0, then I can solve. So I have 4x minus 6. If I set that equal to 0, the 6 will move over. I get 4x is equal to 6. You then divide by 4, and there it is. It does reduce down to 3 over 2, or 1.5. So your vertical asymptote could be x equals 1.5. Notice it is an x equals, because that's where it's crossing the x-axis. All right, the horizontal asymptote, you don't set things equal to 0. You don't do that. What you actually do is you take your leading coefficients, in this case that's going to be the 7 and the 4, and you just reduce them. That's it. So there's your answer. Y equals 7/4. Again, very easy problem there. Now that you have those, the domain and the range are going to be pretty easy here. The domain is going to be negative infinity up until you get to your vertical asymptote, so 1.5, and then at 1.5 you carry on to infinity. Oops, probably put that there. The range is just going to use the 7/4 and go on to infinity. So in a sense, a little bit of a redundant problem. Okay, the other two things that I was thinking of, and you'll see them listed over here, like relevant questions, would be to ask about the x-intercept and the y-intercept. Even though this question doesn't actually discuss it, you might find some value in seeing this part anyway. The x-intercept is when the top is equal to 0. So you're going to notice that we did bottom equal to 0 for vertical asymptote. If you set the top equal to 0, you get something almost totally different here, right? But it's the x-intercept, or if you want to call it a root. So if I took 7x plus 5 and set that equal to 0, that would lead me to x is equal to negative 5/7. So that would have been the x-intercept. The y-intercept is when the x value is 0. So if I plugged in zeros for everything here, you actually just get back the constants. Everything else times by 0 just goes away. So that would be the x-intercept that we would, the y-intercept, sorry. This would be the y. X is going to be equal to 0 to get the answer, but this is the y-intercept that you'd have. Okay, not part of this question here, okay, but just good information you might find useful maybe for the actual graphing part. Okay, last, here's our basic template for a rational function, and what you're getting is a description of an equation and want you to build that. So you need to know the a, the h, and the k value. Okay, from the beginning here, the vertical asymptote is going to be at x equals 7. The horizontal asymptote's at 5. What those have literally done for you is given you the h and the k values. Okay, the vertical asymptote corresponds to the bottom. Also even says x, that kind of helps out there. It does go in as its opposite, and that's why the minus is there. So we're going to have an x minus 7. The horizontal asymptote, the whole thing's been elevated to 5. So you're going to have a plus 5 here. So you're about halfway done. What we don't know yet is the a value. Okay, and that's where this final bit of information comes in. It says that the graph has to contain that coordinate. Okay, so if I plug the 4 in for the x, so I'm just going to erase that and put in a 4, I can set the whole thing equal to 9. And then you do a little basic solving problem here. This is going to subtract to give you negative 3, so you got 9 is equal to a over negative 3 plus 5. You'll have to subtract the 5, move that over, so you're going to get 4 is equal to a over negative 3. You then multiply by negative 3, and a is negative 12. Put it all together. You have negative 12 over x minus 7 plus 5, and that's it. Now, what I hope that you see from this part is these graphs, if you know the rules to them, like how to approach the problems and graph them then, they're really pretty easy. And there's a lot of redundancies as well, like the vertical asymptotes tell you the domain, the horizontal asymptotes tell you the range, sort of stuff. Okay, please make note of this, just in case that shows up. If you have a positive graph, that's where it generally shows up. If you have a negative, then it's going to be sort of the flip-flop. And I think that's it.